You may not be aware of just how frustrating EHRs are to doctors and nurses, and just how angry they are about it. Don't take my word for it. Please ask any doctor or nurse you know. Talk to several. When I talk with my colleagues about EHRs, some are frustrated, some are just resigned and see EHRs as a necessary evil. Few realize what their EHRs could be: their best friend, their helper, a tool they could not imagine seeing a patient without. A tool that thinks like them, anticipates what they need, and has it ready before they ask for it. It's not just me saying this is a huge problem. It's difficult to overstate how bad the situation is. There's a shortage of medical practitioners almost everywhere, yet doctors that use EHRs on average state that their EHR increases their workload and sucks away 30% of their time and 50% of their mental effort. By the way, mental effort is a real thing. The inner sense of mental effort correlates closely with brain imaging studies, and in fact it's well established that humans can only expend so much mental effort before their working memory breaks down. What solutions do we have to offer? First, user interfaces designed for how human providers actually think. Second, underlying medical knowledge bases that enable responsive, dynamic decision support. The state-of-the-art in usability research has resulted in rules like these. You could use these rules as criteria to compare two systems, like A is better than B in preventing use errors because such and such. Unfortunately, EHR companies build these Rube Goldberg systems and then apply the usability rules to try to make them usable. An optimized Rube Goldberg machine is still a Rube Goldberg machine. Basically, the point of all these usability rules is designed for the user's cognitive system. But what does that mean? How does human cognition really work? Well, you can spend years lost in the details of research about human cognition, consciousness, neural networks, and so on. But the basics, as they apply to doing an expert task, can be distilled down. First, layers of neurons form neural networks which encode knowledge. Long-term memory contains about 100 billion neurons arranged in layers, forming neural networks encoding knowledge. This diagram represents the visual perception neural network. Each layer detects features. On the left side, starting with the eye, raw data is collected and presented to this first layer, V1, which recognizes basic features of the data and outputs to the V2 layer. V2 recognizes higher level features and outputs to subsequent layers. The last layer's output results in actual real-world level objects being recognized, in this case, a teacup. Humans don't do well with more than one active task at any time, and the current task sets the context for what she perceives, how she processes it, and what actions she takes. In fact, all the knowledge in long-term memory is encoded specifically to support particular tasks. Perceive, process, act. Here the current task is, make a cup of tea. At lower left is the same perceptual neural network we saw in the slide before last. At lower right is a motor output neural network. The motor output network is kind of the reverse of the perception network. It starts with a high-level action such as put a tea bag in the teacup, which is then translated down through subsequent layers until it goes out to the muscle fibers as commands. The middle layer here is what we're mostly concerned with in regards to user interfaces. This is the expert knowledge, also known as the mental model. It is all the knowledge a human expert has about real-world objects, concepts, relationships, and actions. If you're watching this, you've probably made thousands of cups of tea. We're all experts in this. If this is your expert domain knowledge for the task, make a cup of tea, then the first layer includes objects such as teacups, water, kettles, and spoons. Layers further along include concepts such as put, boil, and pour. No two experts have exactly the same expert domain knowledge, but all experts have the same basic structure to their knowledge and nearly all the same concepts and relationships. So, knowledge is encoded in the layers of neural networks, and networks are organized around tasks. Running even a simple task like making tea takes many cycles to perform all the subtasks. For running through the task cycles, there is a fast, long-term memory path and a slow, working memory path. Perceive, process, and act. These are very fast, high bandwidth, and accurate for well-learned tasks and long-term memory. It's automatic, and essentially no mental effort is required. But when the pattern that arrives here is vague, contains conflicting data, or is just not mapped clearly to some action, then the human brain has to fire up working memory. This illustrates the slow working memory pathway. Executive systems are considered part of the working memory complex and operate upon concepts there, perform searches using them as indexes, switch tasks, even propose and test possible new concepts and new relationships. A quick example. You're trying to make a cup of tea, which you usually do by putting a tea bag in a teacup, filling it with water from the faucet, and microwaving it. You take your teacup with tea bag to the faucet and turn the handle, and no water comes out. Now what? You do not have any well-learned mapping for how to handle this. You will have to fire up the working memory system to deal with it. Working memory can manipulate concepts and relationships to resolve problems. So you're standing there with the teacup and tea bag and no water is coming out of the faucet. Using working memory and executive systems, you can now consider higher level questions such as, should I switch tasks? What's more important right now, making a cup of tea or figuring out what's wrong with the water? If I stick to my current task, where else can I find some water for my teacup? Making decisions like switching tasks and knowledge searches like where else can I find some water and other operations are performed in the working memory complex. Working memory provides a temporary memory buffer for only about 4 concepts at one time with help from these supporting buffers. It takes a lot of mental effort to keep them there, and they degrade in seconds if not being actively manipulated or rehearsed. Executive systems can manipulate them only when they're sitting in working memory. But if the long-term memory system is unable to give an automatic high-probability solution, working memory must be brought to bear. So we have a fast, long-term memory task solution pathway that deals very quickly and effortlessly with well-learned knowledge when the input is as expected. Then we have a slow working memory pathway, which is interruption sensitive, error prone, and that nevertheless will be needed a lot because real-world patients are complex and exceptions from the usual input patterns are the rule more than the exception. Our user interface has to support both these pathways. For the fast long-term memory pathway, the user needs to be able to see the whole pattern, all the concepts in play with a given patient, especially at the transitions from one layer to another. Our user interface system should use its knowledge to offer downstream possibilities. For instance, given some 7 symptoms, what problems are suggested? What diagnoses are suggested? Above all, our user interface should not obstruct the long-term memory pathway. All current EHRs, and it is no overstatement to say this, all current EHRs force users to fire up their working memory just to navigate the complexities of the user interface itself. To support the working memory pathway, we again must track all the concepts in play at all times and have them available on one screen. By doing this, an interruption can occur, which means replacing the user's current task for some period of time, and then the user can return to the original task easily and quickly because the user interface has in effect frozen and held the scenario for him. Okay, how about a task more complex than making tea? The most basic task in medicine is diagnose and treat the patient. In this case, it's a psychiatric outpatient. Using the methods of what's called cognitive task analysis, we discover that a psychiatrist's expert domain knowledge is arranged like this. His thinking flows through the subtasks of gathering observations, considering problems and diagnoses suggested by those observations, gathering more observations to clarify problems and diagnoses back and forth several times, and finally making treatment plans to address the diagnoses and problems. The psychiatric domain knowledge contains several thousand possible observations, several dozen possible problems, a few hundred possible diagnoses, and perhaps 1,000 possible plans. Here I'm showing the ones that a psychiatrist is collecting for this particular patient. I'm also showing a few of the relationships. Decreased sleep suggests anxiety and also suggests depression, and so on. The various problems suggest certain diagnoses, which in turn suggests particular treatment plans. These are the neural network layers of a psychiatrist's expert knowledge. So if a user interface lays out observations, problems, diagnoses, and plans like this, it is matching the structure of the user's expert domain knowledge. By laying out the user interface like this, you are not obstructing fast pathway cognition and decision making. And if working memory must be used, we're automatically capturing and holding all the concepts in play, making the user interface resistant to interruptions. So now consider this typical psychiatric EHR user interface. This one is called Qualifax. It's the first or second largest psychiatric EHR in use in the United States. Thousands of psychiatrists, millions of patients are involved. We could take a long time to talk about this Rube Goldberg user interface, but let's just hit the high points. First, it divides the task diagnose and treat a patient into 10 different screens. The various screens are accessible from the menu on the left side. You can only look at one screen at a time. This forces the user to hold concepts in his working memory while navigating around to different screens. The screen sequence in no way confirms to the user's expert knowledge structure. For instance, observation layer objects are scattered across 4 different screens. It's impossible for a psychiatrist to flow through her expert knowledge structures. This user interface forces the use of working memory for even the simplest of patient encounters. And even as it forces working memory to be used, it does not support working memory by showing all concepts in one place. Information is collected from the user as free text typed into a multitude of text boxes. Free text is not knowledge and cannot be tied to any psychiatric knowledge base, so it's incapable of offering useful decision support. And since it doesn't capture information as knowledge, it's also mostly useless for statistical analysis of patient data. In short, this is a design to force unnecessary use of working memory, overload working memory, and create errors. Now, let's look at a prototype for a user interface for the task diagnose a psychiatric outpatient. This prototype does not have plans entered into its knowledge base yet, so we'll stop with diagnose and not proceed on to plans. First, notice it's all on one page. There is no need to hold concepts in the user's working memory while navigating around to different screens. Second, notice that the layout matches a psychiatric expert's knowledge structure, proceeding left to right from observations, problems, diagnoses, plans. Remember that a psychiatrist's expert knowledge contains several thousand possible observations. The only part of this user interface that requires some learning from the user is this: a scheme to access any of several thousand possible observations with one click. Picking and sorting of objects by hand are subroutines learned by humans at a very young age. And so fast, long-term memory pathways are leveraged as we drag and drop observations. No working memory overhead is required here. We are building a pattern of observations here, ideal for fast, long-term memory recognition of patterns. We can even rearrange them to make patterns pop out. Meanwhile, the prototype's knowledge base is offering possible problems to explain these observations. Since these are system suggestions, they are shown in gray. If the user agrees with one and clicks on it, it is confirmed and shows in black and bold font. This works for both problems and diagnoses. Notice that the system is constructing a differential diagnosis for the user. The unconfirmed diagnoses are not thrown away, they remain as part of the record. As noted earlier, a psychiatrist goes back and forth several times between observations, problems, and diagnoses, in particular gathering additional observations to support or undermine a particular problem or diagnosis. The underlying knowledge base is certainly capable of suggesting which additional observations would be high value in deciding between different problems and diagnoses, although that function is not built into this prototype. Likewise, no plans have yet been added to the knowledge base underlying this prototype, but the pattern will be the same. Problems and diagnoses suggest plan items which will be offered as suggestions. The user can confirm suggested plan items, and there will also be a mechanism to access any of 1,000 or so possible plan items with one click.